Okay, in the last video, we saw how a single weight vector in a linear layer draws a straight decision line in the input space. Today, we are going to add a ReLU function to introduce nonlinearity. So the ReLU is a simple operation. It returns the ledger of 0 and its input. But in this video, I'm going to take it one step further and show you how this simple operation turns a straight decision line into a bent decision boundary. Okay, so we are going to be working with this simple network. In the first layer, we have 2 neurons. The second layer, we have an output neuron, a single neuron. So the output of the first neuron, we can call it H1, output of the second neuron, H2. So here we can know that the weight tensor of the first neuron is 1, 2. For the second neuron, it is 2, 1. The output will just add them and subtract 1. For simplicity, let's say the input is x1 and x2. So we can use a simple rule. If, for example, y of x is greater than or equals to 0, we can say that the input belongs to class 1, otherwise it belongs to class 0. So this is the entire system that we are going to be working with. The next step is to understand the hidden decision boundaries of H1 and H2. So maybe I can introduce this. Today there will be a lot of equations, that's why I printed them. Anyway, so in each neuron in the first layer defines a line where it switches from off to on. And this is the line where really the input to ReLU is exactly 0. So for H1, the pre-activation is x1 plus 2x2. And the switch line for H1 is where, so the pre-activation is Z1. The switch line for H1 is where Z1 is equals to 0. Okay, so just like this. And these are the lines that we're going to be plotting. Now, again, think of the switch line as the place where the neuron is indifferent. So on one side of the line, Z1 is negative, and on the other side of the line, Z1 is positive, for example. Okay, so we are going to plot them. Maybe I can pull this in here. By the way, today I have a lot of plots. So I'm going to plot these two lines. So the blue one is for x1 plus 2x2. The orange one is 2x1 plus x2 equals to 0. Okay, now notice that these two lines divide the space into 4 regions. And this is important. Because really we can ask the question, in each of the 4 regions they create, which neuron is active? So for each of these 4 regions, I can take a sample x1, x2, plug it into Z1 and Z2 and check. For example, if Z1 is greater than 0, I can say H1 is on in that region. If, for example, Z2 is less than 0, I can say H2 is off in that region. So really doing this is going to give us like 4 on and off patterns. So I have this plot, this next one, maybe I can put it here. This plot one for the on and off pattern. So in here both are off, which means that Z1 and Z2 for the points are less than 0. Here both are on, which means that 1 and Z2 are greater than 0. Here it is only H1 that is on. So for any region where a neuron is off, means that the neuron's contribution will be 0 for the output. If H1 is on in that region, for example here, it stays on for all the points in the region. Okay, so far so good. Remember, what we are trying to do is, what we are doing all this is to see how ReLU ends up creating a bent decision boundary. Okay, so maybe I can put this thing here. So all right, now since ReLU can turn off in some regions, the output y of x actually has a different linear formula in each of these 4 regions. Okay, so to keep things short, I won't write all those immediate y of x formulas explicitly. So instead, I'm going to just go straight to the decision boundaries they produce. Remember that the decision boundary comes from setting the output to 0. So y of x equals to 0. So essentially, we're going to trying to find the output result for each of this region, output line for each of these regions. So for example, in here, in this region, I can go back to the original, this one, and set h1 and h2 0. Of course, we have to equate that to 0, and we'll end up with this. And for this our two region, only h1 is on. So essentially, we're going to say h2 to be 0, and we'll end up with these formulas subsequently when we do that. Okay, so essentially, a kind of each region has its own final decision boundary. Okay, so what we are going to do is for all of the lines, we are going to draw them. So that's why we have this plot 3. Okay, we have quite a lot of plots here. So for example, x1 plus 2x2 equals to 1 is from here, and that is the blue one where only h1 is on. Okay, and the orange one, which is, I think it is where both are on, is this one. Okay, x1 plus 2x2 equals 1 over 3, sorry. Okay, now, so in this plot, we have like not only the original lines that we had in dashes, but also the 3 candidate decision lines from the output neuron. Now, these 3 lines are exactly the candidate decisions really come from 3 regions where at least one neuron is active. Okay, we didn't plot something like this because both neurons are off. So ReLU is doing something very powerful here. It picks the linear formula for y of x to use depending on the region. Okay, all right, so far so good. Now here comes the fun part, seeing how the bend actually appears. What we are going to do is we are going to keep only the piece of each line that belongs to each region and throw away the rest. So for example, where only h1 is active, this blue line, it turns out it is only active in this region. So we are going to cut it here and throw away this because it is only active here. The orange line is only active in this region, so we're going to cut it here and throw away this part. The green one is only active in here, so we're going to clip it here and throw away this region and keep this one. Okay, so doing that, we are going to result in something like this. After removing away the lines, the parts of each line that we don't need, we end up with really this beautiful polyline that creates the bends that we have been talking about. Okay, so really above this line, y of x is greater than 0, and below it y of x is less than, sorry, above it y of x is greater than equals to 0, and below it y of x is less than 0. Okay, so this is it. Thank you for watching. Let me know if you have any questions in the comments. Bye bye.